Welcome to this special lecture about Grover implementation, where we will be looking at the logic and explicit construction of the oracle and diffusion operator in the algorithm. If you are interested in a more exhaustive discussion about the Grover algorithm itself, I suggest you to watch the dedicated lecture you can find in the Practical Quantum Computing course with Qibo. Just as a reminder, we mentioned that the Grover algorithm is useful to search for some specific element among many different items. So it's a search algorithm, and it is also known as Grover search algorithm. This task is typically solved classically with a complexity of m in the worst case scenario, where m is the number of items which compose the set in which we do such a research. In quantum computing, instead, Grover helps us in solving this same task with a quadratic speedup. The idea here is to give you some more motivation about why we implemented the oracle and the diffusion operator as presented in the other lecture about Grover. We will do this following a 3-qubit example. Actually 3 plus the ancilla, so 4 qubit in total. Before starting, we want to add a small comment about the Grover algorithm itself. Using the same example we discussed in the other lecture, one of our friends did a joke of spoiling your coffee with sugar, and you would like to find out who is guilty of that. In particular, talking about the implementation, it may seem strange the approach we have to the problem, in the sense that you may wonder, do we really need to search for the guilty person in the room? I mean, we start our implementation defining a guilty index. Thus, we already know the solution. We can associate the index to the element of the list of bit strings, and everything is done. This is true. In this example, we basically know everything from the beginning. This is because we are the guys who are constructing the oracle itself, and we are building the algorithm in such a way we can actually check if it is working or not. In a more real case scenario, you should imagine we have zero knowledge about the solution, while the oracle has. It can be the case, for example, in which you receive an oracle you cannot open, like a super secret and protected file, and the guilty index is set inside the oracle itself, so you actually don't know the index. Then you are allowed to use the oracle without opening it. Well, in that case, you don't know the answer, but you are still able to find the solution with a quadratic speedup, using the oracle in a quantum computing context, thanks to the Grover algorithm. Okay, once made this clarification, we can start discuss more in details the choice we made while building the Grover circuit. Okay, we can start as usual by importing some useful packages. We start from Qibo, import Qibo. It's useful because then we can set the backend. Actually, in this lecture, we are not going to use directly the Qibo modules because they are already implemented and called inside some functions we are going to import now. In particular, from the already implemented scripts, we import. So from scripts, import plot scripts, utils, and Grover. Grover is a collection of functions in which we basically wrote the same building functions we presented in the lecture you can find about Grover in the Practical Quantum Computing course with Qibo. But we still need to set the backend from Qibo in order to define which is the best engine on which we want to run our execution. So Qibo JIT in this case. Fine. Now we can set the problem dimensionality, number of qubits of the input register equal to 3. We can generate our bit strings using a function, which is bit strings equal to utils dot bit generate bit string combinations. Then you set n, and then we can set one guilty index, and so one guilty state. Since we are going to match the oracle you see here in the circuit, you will see the guilty index guilty index will be the number 5. Indeed, if we then print, we can also save it. So guilty state, let me say guilty state equal to bit strings of guilty index. And then you can print it. So print guilty state. The number 5 is the 101. And as you will see, this will be exactly the state which is able to activate the phase kickback in the oracle, acting with this specific oracle here. Okay? Because what we are going to do with the oracle is to apply an X gate where we have a 0 in the bit string. Indeed, this will change the bit string 101 in the sequence into the 111. That's exactly the one who is able to trigger the multi-control NOT gate. But we will be, again, on this concept in a while. So now we can start to see what happens building the Grover circuit step by step. At first, we can build the first layer. So we build a circuit that's just composed of Grover dot build initial layer. We need to pass the number of qubits of the input register. Then we can save the state we get by executing the circuit with exact simulation. And then we can draw the circuit. So print c.draw. As you can see, we have one X gate here, which is moving the ancilla from the state 0 to the state 1, because, as you probably remember, every qubit is by default set in the 0 state. And then we apply the Hadamard's to build a superposition. We can also save the average value of the amplitude of the input register. This is useful just to have a look to what is going on with the amplitudes. It will be more useful during the usage of the oracle. But still, we can say a equal to utils dot compute input register average amplitude, and we need to provide this function with the state. Then it will compute for us the average value of the input register. And yes, we can also print it if you want. Now what we can do is to plot the input register amplitudes. We call plot script dot plot input register amplitudes, and we pass the state. Okay, you see, we have a perfect superposition. You can also add an extra argument, which is average amp value. If you pass AV, then you will also have an horizontal line, which corresponds to the value you computed before. So thanks to you, this compute input register average amplitude. I mean, here it was not very useful. You could extract on your own the value, but will be useful soon. What we can do now, before having a look to the oracle and the diffusion operator, is to plot once the amplitudes also involving the ancilla, so not only the input register amplitudes. This will be maybe useful to understand what's the effect of the sign minus in the state preparation of the ancilla. For doing this, we can call the function plot scripts dot plot amplitudes, and then you can pass the state. What you see is still the superposition, and you can understand it because you see the magnitude of the amplitudes that are always the same. Yes, but when the bit corresponding to the ancilla, the last one, the closer one to the plot, is 1, then you see the amplitude is flipped. Perfect. Now we can have a look to the oracle. As you can see from the diagram, the oracle is divided in 3 parts here, 3 layers. Each barrier here is stopping the oracle at some point. So with 1, we stop it after the execution of the X gate on the second qubit of the input register. With 2, we also apply the multi-control gate. And with 3, we reapply the X gate. Actually, what we want to see is what happens to the amplitude if we stop the oracle with these kind of barriers. With the code, we can do it quite easily because we modified the build oracle function by adding an extra argument depth. And you can simply call it by setting depth equal to 1, 2, or 3. And this will stop the amplitude at the barriers. Perfect, so we can say, okay, our new circuit is C equal to. Okay, we need still the initial layer, so grover.build initial layer, and we set the number of qubits of the input register, plus. Now we call grover.build oracle, and building the oracle, now we need to pass the guilty state, the number of qubits of the input register, and also the depth. We start by setting depth equal to 1. Then we save the state, so state equal to C. We execute the circuit basically, and we call the state property. Then we can also save the average value, so av equal to utils dot compute input register average value, compute input register average amplitude, passing the state, and then we can print the circuit. So print c.throw, and as you can see, we have the same initial layer of before, plus 1x gate applied to the second qubit. So this is exactly the same you see from the diagram. What we expect from this? Under the amplitude point of view, nothing, because we are just changing the name of the components. So the second bit in the bit strings will be flipped. Let's see it plotting the amplitudes. Plot scripts dot plot input register amplitudes and then state. And we can also pass the average amplitude value AV. Indeed, we see the same plot of before. Now we can complicate the example. So what we need to do is to come back to the same cell of before, and now we stop the building of the oracle at the barrier number 2. We can do this in practice by changing depth into 2. So now from the diagram here, you see we add the X gate to the second qubit of the input register plus the multi-controller node. What we expect from this is some phase kickback. In particular, the phase kickback will be activated by the only component of the system which can do that. So the only component is the one in which each qubit is in the one state. What happens if we do this? Actually, it's this. So you flip the 1, 1, 1 component. And as you can see, the average value of the amplitude is now moving down because of the flipped 1, 1, 1. But this is not what we want to do, because our guilty state is not 1, 1, 1, but 1, 0, 1. Let's see if the last missing piece of the oracle will help us in this. What we expect is that if we reapply the X to the state, then what is here, the 1, 1, 1, will become the 1, 0, 1, because we flip the value of the second bit. We can set here depth equal to 3. We re-execute. As you can see now, the circuit diagram is showing that we are also adding the X gate. And if we plot it, you will see the flipped component is moved from 1, 1, 1 to 1, 0, 1. So the oracle is perfectly doing what we want. We can move on with the diffusion operator. This discussion will be a bit longer because we have, as you can see, 6 layers represented by 6 barriers. The first one is very simple. We just add an X gate to the ancilla. Actually, this is not really needed to perform the Grover algorithm, but it's needed if you want to be sure that you are implementing the proper operator, what's called the inversion around the average amplitude. So it's just a matter of being consistent with the theory. But if you look into the probabilities at the end of the problem, then you don't care about this x. Then we add a layer of Hadamard gates. This will be useful to switch from the superposition basis, because we are in the superposition basis, to the computational basis. Then we add an X gate, and this is useful to move the problem from the 000 to the 111, you will see. And then you apply the control not gate. We move again back to the 000, and then we reapply the Hadamard gates. But we can discuss step by step in a more clear way. Again, the bit diffusion operator function is modified so that you can set the depth. So you just set 1, 2, 3, 4, 5, 6, and you will have the circuit built until some specific barrier, as you can see in the diagram. Let's do that. The new circuit is so composed of Grover dot build initial layer, number of qubits of the input register, plus Grover dot build oracle. We pass to the oracle the guilty state, the number of qubits of the input register, and the depth equal to 3 because we want all the oracle, plus Grover dot build diffusion operator n, and then depth equal to 1. We stop at 1. Then we save the state, so state equal to C executed dot state, and we print the circuit. Print C dot draw. Once again, what we have here is the same circuit we had after executing the oracle plus 1x we are applying to the ancilla. So plot scripts dot plot input register amplitudes, and then we pass the state. We have the same situation but flipped. And this is what happens by applying the x. Now we want to apply the Hadamards. The Hadamards, as you know, move the plus state into the 0 state and the minus state into the 1 state. So since many of the qubits are in the plus state, indeed only one of them is not there, we expect to amplify the amplitude of the 0 state, because most of the information is coming back to the 0 state. We are going also to see the effect of this flipped amplitude in the other amplitude of the system. So what we can do is to stop the execution of the circuit until the depth equal to 2. We compute the circuit. As you can see now, we are adding Hadamard gates after the oracle. And in terms of plot, you have an amplification of the 000 state and some remaining state here of a lower magnitude. So we are moving the information to the 0 state in particular. The next step of the diffusion operator is to apply the X gate. This will move the 000 state to be the 111. Indeed, the state in particular, which is acting on the ancilla. So this the component of the state which is able to trigger the multi-control knot. We can stop so the diffusion operator with depth equal to 3. We are adding the x's, and if we look to the plot, you will see a slightly similar configuration. I mean, any 1 is transformed into 0 and any 0 is transformed into 1. The most important thing here is that the 000 state is moved to be the 111. Then we apply with the fourth layer the multi-controlled gate. We expect, so, to receive a phase kickback from the ancilla and to see the 111 state flipped. We can set it 4 here. You see the multi-control gate here, and from the plot you see the 1, 1, 1 state is flipped. Now we need to come back to the same state configuration we had before the diffusion operator. So we need to reapply the X gate to restore the original combination of 1 and zeros, and then we restore again the superposition basis, moving from the computational basis to that one. We can start from the X's, and these move the 1, 1, 1 state in particular to be the 0, 0, 0. And if we set depth equal to 6, then we restore the superposition basis. And what you see in the end is that your target 1, 0, 1 get amplified. The other component of the superposition state with a decreased amplitude. This is actually how the diffusion operator works. I mean, this implementation of the diffusion operator works step by step. Finally, what we can do is to just compute the Grover algorithm with a couple of execution of the routine in order to have a better final result. So, namely, 1, 0, 1 amplitude closer to 1. What we can do is to call a specific function to build the circuit, so C equal to Grover dot build Grover. This build Grover function is basically a function which takes together all the pieces of the puzzle, so the initial layer, then the oracle, and then the diffusion operator, repeating the oracle and diffusion operator as many times you want. You can do that by setting guilty state. Then you should provide it with the number of qubits of the input register and the n steps. In this case, we can set 2, because we have just 3 qubits in the input register. Then we save the state, so state equal to C, open close dot state. And finally, we plot the amplitudes. So plot scripts dot plot amplitudes input register here, and we pass the state. As you can see, the magnitude of the amplitude is reduced. In this case, is negative. This is because the average value of the amplitudes after the oracle was such that the inversion around the average had this kind of effect on the amplitudes. But in the very end, when you look at the final measurements, if you add also the final layer, the one of the measurements, then you look into the probabilities, and so you square these values, and you will have in the end one probability close to 1 and the other probability is even smaller. Okay, with this we can finish this special lecture about Grover. Okay, with this we finish this special lecture about the Grover implementation, in which we opened the black box, both the oracle and the diffusion operator, because I think it was quite interesting at least to understand why we wanted to use these specific gates while building the quantum circuit of the Grover algorithm. So thank you for watching this lecture, and thank you also for having watched the whole practical quantum computing course with Qibo.